Check it out now, y'all.
nanoHUB-U Online Instruction.
Hi, welcome to the second lecture of week 2 of the nanoHUB-U in material science of rechargeable batteries. Today we're going to talk about the electrochemical potential. Last class, we derived the conditions for equilibrium for an electrochemically active system. We found things we already knew, like the temperature between two electrochemical phases at equilibrium has to be the same. We found an interesting relationship. If we have phase alpha and phase beta in contact, their chemical potentials are not equal to each other, but it's the quantity called the electrochemical potential that it's uniform across the two phases, meaning that if you have a chemical potential difference between phase alpha and phase beta, a voltage difference will develop, and that's what we refer to as the material potential, so that this relationship for both component 1 and component component 1 and component 2 holds. Okay. Another way to look at it is by simply rearranging and passing the chemical potentials to the right and the voltage to the left. And so we find that the voltage difference has to do with the chemical potential difference divided by ZF, as it has also been traditionally known. So, and we can think of this potential, say for component 2, if we arbitrarily call that the lithium of the system, the amount of lithium of the system, as the driving force for intercalating. So with respect to, say, the lithium reference, you can think of now our sketch of rechargeable battery, where phase 1 or component, the phase of the anode will have its own chemical potential difference with respect to our reference, and the cathode material will have its own chemical potential with respect to the same reference, say in both cases the lithium reference, and that will define, you can write it in these terms, in terms of the chemical potential divided by ZF for both anode and cathode. And the voltage of the system then, as we defined in last week, would be the voltage difference, or if you prefer, the chemical potential difference between both components for both cathode and anode. And as a result of that, we will get the voltage that the battery will deliver, as you see here. And that will be, of course, a result of the shape of that voltage, which would correspond to that chemical potential, that equilibrium chemical potential, with respect to the reference. This say for this case for a lithium manganese oxide system, and if we subtract that to the voltage that with respect to our common reference that the cathode has with respect to the anode, then we will have the voltage of the cell. Okay, so at this point, of course, the question arises: what is the functional form of that chemical potential, and how is the underlying materials science, the underlying thermodynamics impacting on specifying that shape? From the point of view of designing a battery, you can think of that what you really would like is this potential to be as high up as possible, okay? Or if you prefer that chemical potential difference with respect to the reference to be as large as possible, and you will also want that the width of that regime, the concentration regime, will be also as wide as possible. Basically, we should be able to, by understanding the origins, by looking at how that chemical potential is specified, be able to maximize the voltage and the concentration, the solubility limit that material can deliver. So in order to do that, what we need to do is look back at the fundamentals as to how we can dissolve a solute in a specific phase or in a set of phases at equilibrium, bringing us back to concepts of thermodynamics or free energies of mixing, or thermodynamics of solutions. And well, here you have a sketch of that free energy. Okay, here the vertical axis corresponds the Gibbs free energy of mixing. The horizontal axis corresponds to the concentration of solute. In this case, it was normalized from 0 to 1. And this line over here, okay, it corresponds to the value of average concentration that we have managed to put into our system. Basically, if from the point of view of a lithium-ion battery, how much lithium we have specified, and you can see that as we apply, we put lithium in the system, the free energy will come down, okay, and of course, that will depend on what is the current state of charge. Now, Gibbs, many years ago, proposed a method called the method of intercepts, which allows us from having this graphical depiction specify what the chemical potential is, and that corresponds from drawing a line that is tangential to the concentration that we're looking at. Okay, in this case, that concentration, if we draw that line, where it intercepts the y-axis at a concentration of 0, that will give me a value of what the chemical potential is, and when the concentration corresponds to 100% solute, the intersection of that line with the y-axis will correspond to the chemical potential of component 2. Okay, this graphical technique, it's very elegant because it allows us to, knowing regardless of what the functional form of that Gibbs free energy of mixing is, we can very easily specify that. And if you think about it, if we know the function delta G of M, we know what value the free energy is at that point, basically delta G M naught. Okay, and what we really need to specify is the change, the difference from that value at that point and the change as a result of stretching that line all the way to the specific point. So at this point, since we know the value, we also know the slope. Okay, and that slope corresponds really to the derivative of that free energy of mixing with respect to the composition. Okay, and then it becomes very straightforward. Oh, and of course we also know the concentration. Okay, at that point. So at that point we both know the Gibbs free energy of mixing and the slope or the derivative of the Gibbs free energy of mixing, and that allows us already to specify the entire equation of the line, because now we know that the Gibbs free energy of mixing at this point, which corresponds to the Gibbs free energy of mixing at that point, okay, plus the change as a result of increasing it by that much, by this line, which will basically correspond the delta GM plus this derivative times this distance. Okay, so if you add that, what you will get is this relationship where you can see really calculating the chemical potential of component 2, okay, corresponds to the value of that free energy at that point plus a correction, a linear correction as a result of the distance that we have to traverse in order to find the intersection of that line. We can do the exact same thing for chemical component 1, and in this case we have to subtract 1, instead of subtracting 1 minus n, we have to subtract n, okay, and the correction, the linear correction from that slope. Okay, so if you do that, it would look roughly like this. Again, the Gibbs free energy of mixing minus, because we're subtracting in that direction, delta Gm times n, okay, and that will give you that value. Okay, now mathematically it's very straightforward to calculate that, as compared to going through all the derivations, which, I mean, it's fundamentally it is the same, but it's very elegant to have these descriptions, and so that we can use the graphical construction to specify the equilibrium. Now, here we're just referring to, say, phase alpha. What we really would like to see is the equilibrium of phase alpha with beta, either because it's a reference phase or it's the phase in which the material is coexisting as the battery is discharging. So here, this picture specifically refers to that description, and here in this case we have phase alpha and phase beta in red. Okay, and for phase alpha itself, we can think of, well, let's just draw, just for starters, what the chemical potential say at this concentration. I would like to find the equilibrium between both of them. Okay, in the absence of any voltages. Okay, or any applied voltage differences or electrical charges, and we can say the same thing about phase beta. And in the absence of that electrical charge that the system may have, equilibrium is specified really when the chemical potentials of component 2 for beta equals the chemical potentials of component 2 for alpha, or if you prefer, or at the same time, the chemical potential of component 1 of beta equals the chemical potential of component 1 of alpha, which means that this line has to move to the right, and as that happens, the other line have to move also to the left, so that these two values have to approach each other, and as they do so, their slopes will change, okay? Their values will also be altered until they both come into alignment, into a position where they both basically share the same slope and the same value, okay? So at equilibrium, both systems will not only both systems will coexist, and they will coexist for the case in which they both share the same chemical potential, the same slope, and the free energy then of the system is specified to the left of that composition of where they share the same chemical potential by the blue line, and to the right where they share the same slope by the red line. In between, they really are shared by this common tangent line, and because of that, this construction is referred to as the common tangent construction. Okay, and now that specifying that equilibrium really specifies three regimes of behavior, as I was just saying. One where alpha is the one that dominates, a region in between where alpha and beta coexist, and another one where beta is the only one that it's stable in the system. And the overall free energy of the entire system really corresponds to the envelope of the entire curve. So again, to the left of that curve, you have alpha only existing, only being stable. To the right of that curve, of that common tangent line, beta is the most stable one. And in between, you have a mixing where both of them will share the same free energy. Okay. That really will specify these regimes. Okay, this limit as to where the amount you can put alpha before you start forming some beta, and or if you prefer, a limit where you will have beta and below which you will have alpha, so that in between you have that mixture of alpha and beta, specifying with this a different regime of behavior in where the voltage will respond. And you can think of it, if you remember, we were saying that the voltage of the battery or the electrode material really depends on the composition dependence of the chemical potential. So you can think of, on one side, the chemical potential is varying, then it hits this regime where the chemical potential is fixed, okay? It leaves that regime, and then the chemical potential changes again, okay? As a result of that, what you have is a region where you will have that voltage to be flat, okay? Specifying with that a concentration regime that you can use as a material potential if you manage to maximize its width. Okay? Now, what we really want to know, what we would really like to know, is the width of that regime, okay, as specified by this composition, the height of the voltage that regime will deliver us, given by the chemical potential, and the fraction of how much alpha and beta we have, because one phase will specify a specific potential, and another one will specify a different one, and also the mixture of both structures can specify the stability of the system. So that is done by using something referred to as the lever rule. And what you do here is that, since we already know what the free energy of the entire system is, okay, we know that to the left of n alpha, basically the solubility limit of alpha, we have this free energy contribution that is given by delta Gm of alpha, the free energy of mixing of the alpha phase. And to the right, we have delta Gm of beta as the one that describes it. What we really would like to do is find what would be the free energy in the middle, right along that line, okay? And well, just for the purposes of discussion, okay, let's just arbitrarily say that there's, for an arbitrarily state of charge, some amount of concentration that this electrode has, and as a result of that, that will specify the width in which the system will act. Okay, when you specify that concentration, a fraction of the material will be more stable in alpha, and a fraction of the material will be more stable in beta. Okay, and what fractions will be which will be determined by the free energy as it's described here. Okay, and for that we really can specify what that free energy is by really calculating the equation of the line. Again, since we know what free energy is in that curve until that point, then we can calculate it directly by specifying the composition of the solubility limit and the free energy of the alpha phase. And then we can make a correction from N alpha to N naught by calculating basically a linear correction along this regime, just like we did on the previous slide. If we do that, and if we reorganize those terms, what we find is that we can indeed rewrite things in terms of the Gibbs free energy of mixing of the alpha phase for in the limit of the composition of N alpha, and the same for the Gibbs free energy of the alpha phase evaluated at ends of beta. And these numbers that multiply the contribution from each of those values of free energy really corresponds to the fractions of how much of alpha I have and how much of beta I have. Okay, and those numbers, okay, happen to add up to 1. Okay, and each of those numbers, as they were added, they refer to as the volume fractions. Now, this free energy contribution applies for fixed temperature, and we can redo this thing for different temperatures, right? So, just like in that case, where we have our curve that are common tangent or envelope of both free energies, they can be directly related for the three regimes: one where alpha dominates, another where alpha and beta coexist, and another one where beta is the one that dominates. Can be drawn for a fixed temperature. They can occur, say, at these two compositions at that one temperature. Okay, these 2 points specify 2 points in this temperature versus composition map, so that if I heat up or cool down my sample, will make these 2 points move up or move closer to each other, or spread out, basically go away from each other. Okay? In that sense, when you do that, that will give you a direct comparison as to how this free energy description corresponds to regimes where alpha plus beta, and beta will coexist, and specify how the potential will vary in each compositional versus temperature regime. If you map directly these 2 points into this map, what you could get is a boundary of all those points where the phase alpha plus beta, basically inside this area where alpha plus beta will coexist, outside which only alpha will be stable, to the left of that and to the right of that where beta will be stable. Okay, the specific shape of this curve really depends on the chemistry and the phases involved to specify equilibrium. Okay, but they by themselves allow you to see directly what regions will have two-phase coexistence, and therefore specify what the potential of the phase is. Now, how does the potential of the phase is specified? Well, if we look back, our two-phase free energy construction can be directly related to the free energy. And if you think about it, the chemical potential, when I am on this side of the plot, okay, corresponds to a line that actually intersects this point, basically goes all the way down there, giving me a very, very negative value. And if I multiply by the charge of the electron, which happens to be negative, it really puts it on the other side, right? And as I move this this tangent line down until I reach here, it reaches a plateau, okay, and then it switches sign and goes from in this case very positive to a constant value, and then it goes the other way. Basically, the slope is down there. Okay, or I'm sorry, in this case it's up here, and it just goes up there to infinity, right? So if we plot those intersections as a function of composition, what we will find, okay, is that in regions where I have only one phase, the voltage is gonna not be constant, it's gonna be varying, okay, depending on the value of the chemical potential associated to that. The region where we have two-phase equilibrium, because the two phases are coexisting and the chemical potentials are intending to be flat, that will force the voltage to be flat. And the moment I end up with a smaller amount, or basically I have managed to form completely phase beta, then my voltage will drop again. Okay? So you can see how there's a direct correlation, and it becomes very important to know those limits n alpha and n beta, because if you want to have a battery that gives you the largest possible amount of composition, the largest amount of the solubility limit, these numbers n beta and n alpha, what you want is to be able to stretch the limits of coexistence on where alpha and beta will both of them together be at equilibrium. If you want to increase the voltage, you really want, with respect to your reference, you want to make this plateau to be as tall as possible, and understanding the fundamentals of what that happens then becomes very important. Okay. Now, what I will show you on the next lecture is some examples where this happens and how you can directly correlate the shape of the curve to the phase diagram, as we were seeing in the previous slide, or how directly from the phase diagram you can have a qualitative knowledge as to what the shape of this curve will be. Thank you.